Okay, so let's get started. So let's start with a quick recap. In the last class, we started looking at an example vector space, which is the set of all n cross n matrices. And then on that, we introduced the notion of inner product. What was the inner product? Trace, right? And then we saw that this induces a norm called the Frobenius norm. So what is the Frobenius norm? What is the Frobenius norm? Hmm? Yes. What is the Frobenius norm? Hmm? What is the Frobenius norm? Yeah, what is that? So suppose I give you a matrix, how do you compute the Frobenius norm? Of course, one way is you take A transpose A and then take the trace of that square root, but uh, without that, so what is it that you'll be doing? No, you'll be squaring each entry, adding them and taking the square root, right? That's all you are doing. So that's what Frobenius norm is all about. Is that fine? Okay. So then we introduce to the notion of the orthogonality, right? So what do you mean by two vectors being orthogonal? Well, based on our intuition in R2, which is V transpose U is 0, right? So if you take the dot product, you should get 0, right? You will get 0 if they are orthogonal. Based on that, we generalized. We said instead of dot product, you take inner product. You say that if you take two vectors or 2 points from a vector space and take inner product, and if that inner product turned out to be 0, then we say that the two vectors are orthogonal, right? And then we saw this notion of how to get orthogonal vectors, right? Suppose I give you v1 v2, right? It need not be orthogonal. So how do you get the corresponding orthogonal vectors that span let's say v1 that's the span of which is equal to the span of v1 v2, right? So what did we do? What is that procedure called? It's called Gram-Schmidt's orthogonalization procedure, right? So we used Gram-Schmidt's, right? So of course, in the last class, I came up with so this method essentially gave us what is known as orthonormal. So there is another easier or straightforward way to come up with orthogonal, and then you can normalize it. Okay, so that's what we will see quickly. So and also there are other variants of finding these alphas or finding the orthogonal vectors. One can pose it as an optimization problem and so on. That is something that we looked at in the last class, right? So finally, we looked at QR decomposition. So we will revisit some of them. So first of all, let's look at, um, for example, let's look at the standard. So ortho, the notion called projection, right? So what is a projection? Suppose you have a vector like this. Let's say you have V and U, right? So what is a projection? So essentially, this point is the inner product. This vector is your projection, right? Do you agree? So how do you find this vector? Of course, if you look at this is alpha times u, right? So I scale alpha, I get this point. I want this alpha u to be orthogonal to this vector, right? So want alpha u to be orthogonal to this vector. What is this vector? V minus alpha u, right? So V minus alpha u. I want this to be 0. That means I can find alpha such that this is satisfied, right? So that will give me the vector. So what is that? It will be alpha times uv. I've used linearity of inner product minus alpha square times u inner product with u equal to 0, right? So this implies the alpha star will be uv divided by uu, right? So this is what we get. So that means the projection of v onto u, right? So for example, if I want to project, let's say v onto u, right? So this is the notation. So what is the vector that I get? It's alpha star u, right? So what is alpha star? U v divided by u u times u. Is that fine? So note that projection of v onto u is denoted by this. So it's uv divided by u times u is what the projection is, right? So how do you get the orthogonal vector here? So what are the orthogonal vectors? U is an orthogonal vector. So for example, u, if you take as is, what is this thing? This is v minus projection of v onto u, right? So this difference, these two are orthogonal. Do you agree with this? Right? Okay. So let's try to generalize this. Suppose I have three vectors. So what should I do? Given, let's say v1, v2, v3. So what is the first step? So I should get the first vector. I'll take v1 tilde as v1 itself. Okay. So what should I do for v2 tilde? Exactly what I did before, right? It's v1. So v1, so essentially I took u and then I took v2 and project onto v1, right? It will be v2 minus project what and what? v2 on v1. Well, I'll just take it as tilde, okay? Because v1 tilde is same as v1. Is that fine? So clearly v1 tilde and v2 tilde are orthogonal. They are not orthonormal, okay? So they are orthogonal. So how do you find v3 tilde? You understood the procedure, right? So for example, v3 is this, and I have gotten, let's say these two are, this is v1 tilde, this is v2 tilde. Think of v3 is in the third dimension, okay? Now how do you find v3 tilde, which is orthogonal? So first I can project it onto v1 tilde, project onto v2 tilde, sum them, I get a vector which is here, right? This will be the vector, right? So I take the difference of v3 and this vector, right? So this vector minus this vector, right? So you take the difference of the two, I get the orthogonal. Do you agree? So what does that mean? It's v3 minus, I want to project v3 on v1 tilde minus projection of v3 on v2 tilde will give me v3 tilde. Now we can verify that v1 tilde, v2 tilde and v3 tilde are orthogonal. How do you verify? You take the inner product and see if they are orthogonal, right? You will get 0 or not. You can easily verify this. Okay. Do you want me to verify or you will verify? So how do you generalize this as Gram-Schmidt's? Now I can just do this, right? Suppose I have Vn, okay, and I can do this, right? So what happens to Vn tilde, which is Vn minus, I have to sum all the projections, right? So I'll sum it from I equal to 1 to n minus 1 because I have tilde v2 tilde for v3. So projection of Vn on Vi tilde, right? Do you agree? So how did you get Vi tilde? Well, this is recursion, right? So maybe I'll instead of Vn, I'll do this. Okay, I'll write it as Vj. This is Vj. Okay, this is Vj. Okay, so basically J is 1, 2, etc. n. If I substitute J equal to 1, I get back the first step. J equal to 2, I get the second, and so on. Okay, this is a simple orthogonalization procedure. Nothing fancy or anything, right? So purely based on our high school geometry. We just abstracted it out, right? We just generalized some of the things. That's all. Okay. So if you are given, this is called Gram-Schmidt's, right? So this is nothing but Gram-Schmidt's, right? So Gram-Schmidt's orthogonalization procedure. So how do you get orthonormal? So first of all, you have, let's say, V1, V2, etc., Vn. You apply Gram-Schmidt's orthogonalization to get V1 tilde, V2 tilde, and so on, Vn tilde. And then if you want to get orthonormal, all that I have to do is normalize, right? So what should I do? V1 tilde divided by 2 norm, and so on, Vn tilde divided by 2 norm of Vn tilde. So I get an orthonormal vector. Okay. Okay. So one thing to note here is that what is this? So let me recollect this. So what is this? How do I write this? V3, I have to project it onto V1. So first V1 tilde. So it's V3 V1 tilde divided by V1 tilde V1 tilde V1. Okay. Remember, it's some constant times V1 tilde. Sorry. Projection of U onto V is some constant times V. Okay, so keep that in mind. Okay, now what is QR decomposition? So QR, that's easy, right? So what is QR decomposition? So you take any matrix A, right? I can think of this as these column vectors, right? A1, A2, etc. AN. Well, remember, this is not this is true for any matrix, okay? Not necessarily square matrix. You can take fat, tall, whatever, right? So I can write this as what? If I apply Gram-Schmidt's orthogonalization, so what can I do? I'll write A1 as some constant times A1. Why? Because if I'm looking at orthonormal, then I want to normalize A1 to get unit norm, right? So this will be alpha A1. Okay, let me call this as alpha 11 A1. Okay, so let me write it like this. So how do I orthogonalize, right? So this is what I do, right? So I how do I do orthogonalization? Let me not even do ortho. Just let me do orthogonalization, not orthonormalize, right? A1. So what happens to the second one? A2. So how can I write A2? So what is the procedure? You took this, and then how did you get the second one? So it's a linear combination of A1 and A2, right? Do you agree? Or sorry, it's not A1. So let me call this as A1 tilde. Okay. So it's A1 tilde and A2 tilde. Do you agree? So this is alpha. Let me write this as 2 1 A1 tilde plus alpha 2 2 A2 tilde, right? This will give me the second vector, which is orthogonal to A1 tilde, right? You understood, right? So A2 tilde, how did we get V2 tilde? V2 tilde is V2 minus projection of V2. So projection is nothing but in terms of V1, right? V1 tilde. V1 tilde is actually some constant times V1, right? So essentially, it's a linear combination of V1 and V2. V3 is a linear combination of V3, V1 tilde, which is V1, and projection of V3, which is V2, right? So on to V2 tilde. So it's a scale version of V2 tilde, which is some linear combination of V2 and V1. Therefore, overall, it is a combination of V1 and V2, right? Is that clear? So this is what we get here, right? So I can write this and so on. What will be the last one? Alpha N1, A1 tilde, and so on. Alpha N, so AN tilde or AN, right? So this is what we get. Do you agree? The last one is a linear combination of all the previous, right? So that's what we get, right? Is that clear? So what will be the last one? Vn tilde. It's Vn minus something, right? So it will be a linear combination of all Vn's or Vn tilde, whatever you want to call it. So essentially, I can write this matrix as what? So this matrix turned out to be, what is this matrix? So if I look at A times X, right? So if you look at AX, so this is a vector. Do you agree? Matrix times vector is a vector. So if you look at the first entry, what does that correspond to? Or if you look at this whole vector, I can write it as linear combinations of columns of A, right? Do you remember that? So I can write it as linear combinations. So what will be the coefficients? Coefficient will come from X, right? So what do we have here? These are all linear combinations, right? Of some A1 tilde, A2 tilde, and so on. So how do you get this? How do you get this? So it's essentially, I can write a matrix. So basically what happens is, so what do I get here? I get a Q matrix, right? This is your Q matrix. Do you agree? This is your Q matrix. Because they are orthonormal, right? I have orthonormal this. How did I get this? Some linear transformation of A, right? What kind of linear transformation? It turns out to be some sort of an upper or lower triangular. Okay, so essentially what it means is that I can write A as Q times R. Okay, so what is this Q matrix? Q matrix is basically, let me write it as this: Q1, Q2, Qn. Of course, whatever we did so far, we just orthogonalized it. You can also orthonormalize it, right? So again, it's basically the effect is multiplying by a constant, right? Normalization. So this has the following property. Okay, so if you look at, for example, Q1 or Qi transpose Qj, that means if you look at the dot product of two columns, right? Inner product of two columns, it will be 0 for all I not equal to j. Okay, you take any two different columns and take the inner product, you will get 0. That means they are orthogonal, right? So of course Qi transpose Qi is what? Is 1 for all I. That means Q1 transpose Q1 is 1 because we have orthonormalized, right? So I can write A as Q times R. What is R? What is R? Hmm? R is a matrix like this. Okay, so it's an upper triangular matrix. It looks like this, and a 0 here. Okay, fine, fine, right? So everyone, is that okay? So why is it useful? So keep this in mind. Even if the procedure is not clear, it's okay. I can always write, given any matrix A, I can write it as Q times R. Q is an orthonormal matrix, the columns wise, and R is an upper triangle. So why is it useful? So suppose I have an equation Ax equal to B. I can write A as QRX. Remember, which is easy, right? You have to find those coefficients, that's all. So now, what is the inverse of Q? Suppose Q is a square matrix. What is the inverse of Q? Okay, let's look at this. What is Q? This is Q, right? QL. What will be the Q transpose? This is Q, by the way. What will be Q transpose? I have to make the columns rows, right? So I'll have like this. This will be Q1 transpose, right? This will be Q2 transpose, and so on. This will be Qn transpose. What do I get? See, Q1 transpose times Q1 is 1. So I get 1 in the 1, 1 position. What is Q1 transpose times Q2? 0. What is Q1 transpose times Q3? 0, and so on. What is Q2 transpose Q1? 0. What is Q2 transpose Q2? 1. So essentially what you get is an identity matrix, right? So if I pre-multiply this whole equation by Q transpose, that is Q transpose Q or X equal to Q transpose B. See, all that I'm doing is multiplication, okay? So I'm just taking Ax equal to B multiplying by Q transpose. That means I have to do QR decomposition, multiply. So what can you say about this? This is identity, right? So what do we have? We have, I'll call this as B tilde, okay? This is another vector. So what do we get? Rx is B tilde. Fine. What is Rx? It's easy, right? So this is the kind of matrix that we'll have. X1, X2, xn. This is b1 tilde, b2 tilde, bn tilde. Now, how do you solve this problem? Well, you should not, we should exactly go in the opposite direction. Let's start with this. There is only one term here, right? When you multiply, so this is entire 0. So when you multiply this, what do you get? This number gets multiplied with xn, right? Okay, so let me call this as Rnn, okay, because this is the nth entry of R matrix, times xn is bn tilde. How easy is that, right? So I know what xn is, right? bn tilde divided by Rnn. So now what happens to this next row? You have these, the diagonal entry and the off diagonal. It's xn minus 1 comma xn minus 1, right? That's xn minus 1 comma n minus 1. That will be the entry. Sorry, why did I? It's R n minus 1 comma n minus 1, right? It gets multiplied by xn minus 1 and xn minus 1 n gets multiplied by, sorry, why did I say that? This is Rn minus 1 n gets multiplied by xn, right? This gets multiplied by xn minus 1. This gets multiplied by xn, right? That is equal to bn minus 1 tilde. Now, how do you solve this? See, I know xn, right? I'll substitute this here, right? So I'll get a number, right? I know Rn minus 1 comma n, multiply that. So take the entire thing to the other side, divide by this thing. So I'll get xn minus 1. You can recursively do, and it's as simple as that, right? So you don't need to find inverse of a matrix and all that. It's computation wise straightforward, right? Is that fine? That's why QR decomposition pretty easy. Okay, everything is fine. Okay, so okay, so at least we have done one decomposition, right? So which is QR, right? We have not studied any other decompositions, so we will see a few more, maybe at least two more decompositions. Okay, any questions? I'll pause for a minute, and if you have any questions, feel free to ask, and we'll move on. Any questions? The good thing about this is, there is QR decomposition for any matrix you give. Okay, there is no condition on the matrix. Okay, so of course, if you have, let's say, two. Let me ask you this now. Suppose I have A1, A2. Okay, so what is the size of this? N cross 2, n rows and 2 columns. So what do you think will be the QR decomposition? What do you think is a QR decomposition? Huh? See, A1 belongs to Rn, right? So in Rn, I'll have n basis vectors, right? I can have n basis vectors. Do you agree? So first one will be scaled version of A1 itself. Second one will be linear combination of A1 and A2 to get a normalized vector which is orthogonal to normalized A1. What about A3? Well, orthogonal to both but living in R3, right? Rn. So I can keep on doing that to get the entire set, right? So I can do, for example, this is Q1, this is Q2. Well, Q1 and Q2 are related to A1 and A2. After that, you just go in the orthogonal space, right? Whichever vector you pick. So you have Qn here. What is the size of this? N cross n. What should I get now? I should get n cross 2. Now what should I multiply here? It's 2 rows and n columns. You agree? Or sorry, n rows and 2 columns, right? You agree? So that means I should have a very tall matrix, right? Something like this. N rows, 2 columns. Okay. Now what should be the entry here? Well, it should be a lower triangular, right? So what will be the triangle? This is, right? There is a 0 here and there is a 0 here, right? Only these two entries, this will be non-zero, this will be non-zero, and this will be non-zero, right? That's all. Do you agree? Okay. So that's what it turns out to be. Okay. Depending on how you write it, so of course I can also write it as a lower triangular if I take the transpose and so on, but it doesn't matter. So is that clear? So the remaining will be 0 because all the other columns here will get multiplied by 0 and it doesn't matter, right? It will add 0 to the resultant. So that means there is no vector component of a1, a2 lying in that span. So the coefficient should be 0. Okay, is that intuition fine? So how many of you are comfortable with MATLAB? All of you are okay. Those who are comfortable with MATLAB, probably I'll give a few computation like this and programming assignment. Those who are comfortable with any other language, for example C, whatever, right? So you can use that, any language that you are comfortable with. Okay, is that fine now? Okay, so now let's move on. So let's look at one more very important notion, which is the following. Suppose I give you a vector. Okay, so let's look at two dimension again. Suppose I give you a vector v and I multiply on the left by the matrix A. So that means I'm considering AV, right? So what is the effect of AV? Huh? What will be the effect of AV? What will AV do? So V is in, let's say 2 cross 1. AV will also be a 2 cross 1, let's say it's a 2 cross 2 matrix. What is the effect of multiplying a vector by a matrix? What will happen? You'll get another vector, right? AV is another vector in R2. So that means, let's say it is somewhere here. This is AV. So by looking at this picture, it's very easy, right? So you multiply by a matrix A, then all that it does is it will rotate, right, by some angle, and it will shrink or expand, right, depending on what the vector is, right? For example, if I operate, let's say, let me call this as A1, but if you operate, let's say A2, A2 will do this on the vector, right? It rotated by a large amount. Not only that, it increased the length also, right? That's how I can think of, right? Now, what is it that you will observe about A1, A2? So just looking at what happens to V, right? So it rotated the vector by less than 90 degree, right? A1 rotated the vector by less than 90 degree. So that means this is your orthogonal to V. And now if you take inner product of AV with V, what do you get? A positive number, right? Do you agree? So whenever A rotated the vector by less than 90 degree and take the inner product, you'll always get a positive number. What happened to A2V? A2V, the situation is quite different, right? Maybe I'll not write it like this, okay? So A2V, uh, this is A2V, okay? Now, what is the impact of it? So if I take the inner product, what do I get? This is the inner product, right? It's negative. Do you agree? So now, suppose this matrix is such that you take any vector V, operate A, it will not rotate more than 90 degree, right? Suppose I choose such a matrix, right? What is the situation? So you take any V, for any V, right, in Rn, in general Rn or R2. If you look at AV and inner product with V, so what is the inner product? V transpose, right? V transpose AV. So what is this? This is V transpose AV or AV whole transpose V. Both are same, right? V transpose AV, right? Is that clear? Okay. So now this is positive, right? What does that mean? So you take any vector, operate A and take the dot product, it will always remain positive, right? So we will give a name for such matrices. We will call that as what? Any idea? Those who have studied matrix theory or maybe um, some data analysis, some online course, you would have studied such matrix, right? Any idea? Huh? Okay, it's called positive semi-definite because it's greater than or equal to 0. If it is greater than 0, it's called positive definite. Okay, so let's define that, right? So this is definition. Matrix A belonging to Rn cross n is said to be positive. Okay, I'll write semi-definite if for every x that you take in Rn, x transpose Ax is greater than or equal to 0. Okay. If it is strictly greater than, we call it as definite. Okay, so maybe I'll write it in color. So if it is this, then you get this. Okay. What is negative semi-definite? It's easy. It should be less than or equal to 0. What is negative definite? Less than 0. Or the other way of saying matrix is said to be negative semi-definite if minus A is positive semi-definite. Okay. Same thing. Is this fine, everyone? Okay, positive semi-definite. Okay, now what can you say about such matrices, right? What about the entries of such matrices? Suppose I say that A is positive semi-definite. What can you say about the entries? Huh? Can you talk about the entries of such matrix? I mean, what can you say about the entries? Huh? Any idea? Can you say something about entries or whatever, right? Let's see. Let's look at an example. Okay, so suppose I have A11, A12, A21, A22. So simple 2 cross 2 matrix. Let's say this is positive semi-definite. Now let's see what happens if I multiply by 1 0. See, 1 0 is any x, right? So, and I transpose. What do I get? When I multiply this, I'll get A11, right? So this, when I multiply, what do I get? A11, A21, right? When I multiply by 1 0, what do I get? A11. But what is our definition? It says it should be greater than or equal to 0, right? Do you agree? So that means A11 should be 0, greater than or equal to 0. That is one thing. What can you say about A22? Well, instead, if I use this, instead of this, I use this, right? What do I get? It selects A12 and A22, and then when you multiply this, it selects A22. So similarly, A22 is greater than or equal to 0. So if I take n cross n matrix, how do you generalize? I can take 1 0 0 0, 0 1 0 0, 0 0 1 1 1 0 0, and so on, right? So if I multiply, what do I get? All the diagonal elements should be positive, right? Non-negative, right? So that is one of the characteristics of a positive semi-definite matrix. So suppose I give you a matrix, now you know how to identify, at least you can rule out. So suppose I give you a matrix with one of the diagonals being negative and some of them being positive. Can you for sure say that it's you can for sure say that it's not positive semi-definite, right? Okay. Now, if it is positive definite, then it should be non-negative, meaning it should not even be 0, right? 0 is also it should be avoided, right? Is that fine, everyone? Okay. So this is one quick check whether a matrix is positive semi-definite or not. Diagonal should always be non-negative. Okay. Let's look at another example. Okay, so this is an example in probabilities, right? So suppose x is a random vector. You know what a random vector is? Huh? You know what a random variable is, right? You take a collection of those. For example, x1, x2. You take n random variables. Okay, it's a random vector. That's all. Okay. So x1, x2 could be correlated. In fact, x1, x2, and so on, xn can have a joint distribution, or it can be IID and so on, right? It doesn't matter. So you have n random variables put together, it's a random vector. Okay, now you have a random vector, right? So how do you generate random vector? There are many ways, right? So for example, if you want to generate a two-dimensional random vector, what you do? For example, you take a circle, a unit radius, randomly pick one of these points, right? That will be a realization of a random vector, right? So it's a realization. That's how we can generate. Okay, so you have n random vector. I call that as x. So typically, I'll write it as x transpose because it's a column, right? Sorry, x is a column. How do I write this? Okay, so yeah, x transpose. So x is basically a column vector. Okay, so I'll write it like this. Now I look at xx transpose. What is this? X is an n cross 1 vector, right? N rows 1 column. X transpose is 1 cross n. So you'll get an n cross n matrix, right? I take expected value of this. Okay, so before that, I'll also assume that expected value of x is 0. You know what expected value is, right? It's expected value of each component. Expected value of x1, expected value of x2, and so on, expected value of x, and you get another n vector, n length vector, which is deterministic, right? So you have all zeros. Okay, this 0 is all 0 vector. Now, what is this called? What is this called? Any? Hey, you should have studied this in your probability theory. No? Yes or no? Okay, at least say, okay, yes, no, I don't remember, don't care. At least you should have one of the four answers, right? Or I don't want to answer. Okay, I. Huh? Can somebody tell me what is the answer? Yes. What is this called? There's a name, right? This is called covariance matrix. Right? It's called covariance matrix, right? So now, if you take a covariance matrix, see, this is a matrix, right? N cross n. I'll call it as sigma. This is a matrix. Now, what can you say about this matrix? Is it positive semi-definite? One thing is sure, right? So maybe I'll use a different notation for this. I'll call it as capital lambda. Okay, this is capital lambda. Now, what can you say about lambda? Is lambda equal to lambda transpose? Is it symmetric? This is called symmetric, right? Is it symmetric? Easy to prove, right? So what is that? What is lambda transpose? This is, you take expected value of xx transpose whole transpose, right? That means you are taking expected value of each individual elements of this matrix, right? That's what you're doing, and you're taking the transpose. That is same as the transpose of xx transpose, but that is same as xx transpose, right? X transpose transpose is x itself, right? You make columns to rows and rows to columns again, then I'll get back the original matrix, right? So this is lambda. Symmetric is one very important property. What else can you say? Is it positive semi-definite? Huh? Why? How do you prove that? Huh? Okay, so take any vector. Let's try this. Take any vector v in Rn. Then let's see. V transpose lambda v, right? I want to show that this is non-negative, right? So what is this? V transpose expected value of xx transpose v, right? So if it is a deterministic, expected value of a times x is a times expected value of x, right? You can pull out the constant out or in, it doesn't matter. So I can write this as expected value of v transpose x, x transpose v. Okay, what can you say about these two? V trans x is a column vector, V transpose x is a number, right? X transpose is also a number. But X transpose V and V transpose X, what is the relationship? Both are same, right? If you take the transpose of V transpose X, I'll get X transpose V. But X transpose V and V transpose X are both numbers. So transpose of a number is a number itself. So they are same, right? So this is nothing but whole squared. So if you take expected value, you take any number and square it, you will always get a non-negative number, right? So if you take expected value of that, it should always be non-negative, right? Well, if you want to be really precise, this V transpose X will always be non-zero almost surely, right? So anyway, so is this fine? So this is true for any, you take any vector V, so it's true. So therefore, it's a positive semi-definite. Okay, so let's look at one notation. A is positive semi-definite. So I'm going to use the following notation, okay? Okay, not greater than or equal to, just like with a, okay, math cal kind of a greater than or equal to. Okay, so this is fine. Okay, clear? Now, we have a positive semi-definite. Intuitively, you understood what is positive semi-definite, right? So it won't rotate by more than 90 degrees in the positive direction, right? Of course, in the negative means it has rotated this way more than 90, right? So it can never happen. Okay, now, what are the properties? If A and B are positive semi-definite, right? Then alpha A plus beta B is also positive semi-definite. How do you prove this? Can somebody try proving this? How do you prove? I should take a vector V. V transpose the matrix times V should be non-negative, right? So let's do that. Take any V. That's what we'll start. Take any V in Rn. V transpose alpha A plus beta B times V, which is alpha times V transpose AV plus beta times V transpose BV. Okay. Now, what can you say about each of the terms? This is greater than or equal to 0. Why? This is greater than or equal to 0. Why? Because A and B are both positive semi-definite. But now, if I want this to be greater than or equal to 0, what do I need to have? A provided alpha, beta are both positive. Okay, R plus is basically positive numbers, non-negative numbers. Okay, so it's positive semi-definite. So I can take any linear combinations, non-negative linear combinations. It will always be positive. Okay, so positive semi-definite. The same is true for negative semi-definite also. It will be less than or equal to, and so on. Okay. What about AB? A is positive semi-definite. B is positive semi-definite. Can AB be positive semi-definite? Huh? Okay, so question. If A is positive semi-definite, B is positive semi-definite, implies AB question mark. If not, come up with the counter example, right? State a counter example. If it is true, you should be able to prove. Okay, so I'll leave this as homework problems. Figure out whether AB is a positive semi-definite matrix or not. Okay. Okay, fine. So, any questions so far? I'll pause for a minute. Any questions? Any questions? Those who are online, any questions? No? Okay. No questions? Fine. Is it okay? Okay, so now let's look at um, so there are two things that we have, right? So if you have a matrix, what are the characterization now? So it can be square or it can be rectangle, fat or tall matrix, right? Or it can be a symmetric matrix. It can be positive semi-definite, negative semi-definite, positive definite, negative definite, neither, right? What do you mean by neither? For certain vectors it's positive, certain vectors it's negative. So then it's neither, right? So now we have so many things, right? So many different varieties of matrices you have, right? So again, our main motivation for studying these decompositions or whatever is to solve algebraic equations, right? So suppose I can write this. I think I motivated this in the first class itself. What is the motivation for um, what is called eigenvalue decomposition, right? So what is eigenvalue decomposition? Again, I'll come back to this in detail, but this is how it looks like, right? U lambda U transpose. By the way, if A is like if it has complex entries, it means U lambda U Hermitian is what we should look at. Okay. So now, what kind of a matrix is U, right? So that is something that you should always remember. So U is, let's say, U transpose is same as U transpose U, which is same as identity. Remember Q matrix when we looked at it? Q transpose Q was identity, but we didn't know whether Q transpose is identity. So what does this mean? This means that the columns are also orthonormal, rows are also orthonormal. That's what it means, right? So this means rows and columns are orthonormal. Both are orthonormal, right? So such matrices are called what? They are called unitary matrix or orthonormal matrices, right? Such, I'll probably write it as Hermitian, okay, because it can be complex also. So I'll just write it like this. So what is Hermitian? So remember, orthogonality of a complex vector is what? It's not V transpose V, it's V Hermitian V. Sorry, V1 Hermitian, V2 is 0. That means V1 and V2 are orthogonal. It's not V1 transpose V2. Okay. So such matrices are called unitary matrix. Okay. Okay, now let's see what is the implication of this. Okay, well, you can solve the ax equal to b equations very easily if you have an eigenvalue decomposition. But let's look at this in greater detail. Okay, u lambda u transpose. What I'm going to do is I'm going to multiply by u on both sides. Okay, what do I get? So u transpose u is what? Identity, right? So what do I get? I get AU is U lambda. Fine. Okay. Let's expand this. So this is, I can write it as A times U1, U2, UN. Okay. Times this is what? U1, U2, UN. Times what is lambda? This will be lambda 1, lambda 2, lambda n. 0 here, 0 here. This is how it looks like, right? Let's concentrate on the first column of the left hand side. What is the first column of left hand side matrix? AU1, right? AU1 is the first column, right? What is the second column? AU2, and so on. What is the last column? AUN. Very clear, right? So what is the first column of on the right hand side? What is the first column? How do I write the first column? See, when you multiply this by the first column here, right? So when I multiply this by this, what do I get? This lambda 1 gets multiplied with first entry here, right? If I want to get the second entry of the first column, I should take this and multiply by this. What do I get? This lambda 1 again gets multiplied by the second entry here. So and so on. So essentially, if you look at the first column, lambda 1 is getting multiplied to u1, right? So it will be, what will be the second one? Lambda v. Okay. Now if I match, so what do I get? I get AUI is lambda I ui. Right? This is what I want, right? So that means diagonalization is essentially, it boils down to this question, right? Whether I can find an u1 or ui's such that AU equal to lambda u, right? So now a natural question to ask is, when can we have a V in Rn such that AV equal to lambda V, right? This is the question. Okay. So now let's answer it in many different ways. So what can I say about this? If this happens, then AV minus lambda V is 0, right? This is true, right? I can also write this as, if I take V common, it will be A minus lambda times identity V should be equal to 0. So what does this mean? So if I call this matrix as A lambda, right? So A lambda V is 0. That's what I'm asking, right? So what does that mean? What can you say about the rank of A lambda? Can it be full rank? No, right? It cannot be full rank. So what is the implication of that? Okay, something that I haven't taught. What can you say about the determinant of that matrix? Huh? Determinant should be 0, right? So determinant of A minus lambda I should be equal to 0, right? Do you agree? So that means this gives me a way of finding a lambda at least, right? So I can find lambda by this equation, right? So I can, this will be a polynomial in lambda, right? So if you look at A minus lambda I, it will be like all the diagonals will be shifted by, it will get subtracted by lambda, and you have that matrix and you have finding the determinant. So it will be a polynomial in lambda, right? It's a polynomial equation, and you get it to 0 and find the solution of a polynomial. So when can you have a solution for a polynomial? Is it guaranteed all the time? See, this is a practical problem, right? So I want to find AV equal to lambda V because I want to solve some linear equation, right? That led to all these. So now what is the fundamental question? So can we have, suppose I give you ax square plus bx plus c equal to 0. So do we have a solution all the time? Huh? Why? Well, it depends, right? What kind of solution you are asking. Are you asking for a solution in R or C, right? Complex or real? If it is complex, fundamental theorem of algebra, right? It says you always have a solution, right? Although the proof is analysis based, not algebra based, but that's a very interesting thing. Fundamental theorem of algebra has a proof in calculus. Okay, anyway, so you always have a solution in C, but what is it that we need? Well, let's say we need a solution in real, right? So that's a fundamental question that you will ask here. So when will you have a solution that is real, right? When can we have a real lambda as a solution, right? There is another question, right? Now suppose I found a real lambda as a solution, then how do you find V? Then it's easy, right? So AV equal to lambda V, and I have to solve for V, right? In other words, I have to solve for this equation. I know lambda. That's an easy thing to do, right? So you have a bunch of equation, you can do row, whatever, elementary operations to figure out what V is, right? That is something that you can always do. So that will be your eigenvector. Normalize it, you will get a normal, unit vector as your V. Okay. Now let's, in order to address some of these, let's make one critical assumption, so which we will continue in the next class as well. So we'll focus on symmetric matrices. Okay. What do you mean by that? That is, A equal to A Hermitian or A transpose if real. So we will look at such matrices and see what is it that we can expect out of this. Okay, and then we will see certain properties, and then we will look at what eigenvalue decomposition is and what are the consequences of that. Then we will look at more general stuff. For example, there is something known as SVD, singular value decomposition, which give me any matrix, I can do SVD. But if I give you any matrix, you cannot do eigenvalue decomposition. May not exist. Okay, that's the power of singular value decomposition. There are other decompositions like Jordan and so on, but we will not get into that. That's another course, right? So maybe you should take a grad level course on linear algebra offered by Rajshekhar and myself. Maybe you'll see more about such decompositions there, not here. Okay, with this I will stop. Any questions? Okay, so this week we will sort of complete the linear algebra aspect of data analysis, but whatever is required for data analysis, and then we will move on to optimization. Okay, so we will also give a few homework problem relating some of the things that you have studied to data analysis, but otherwise we will conclude this week. Any questions? And reminder on quiz. So be prepared. Whatever I'm going to cover till Friday, it will be there for your quiz, right? Go through the notes. Okay. Any questions? If not, we will stop here.